So couple of questions. Oh, you got a paper 3 this time around as well, right? Okay. Yikes. Okay. There we go. All right. Which one should I go through? Yeah, let me look at one first. 0.5 temperature falls from. Oh wow, it's actually not easy. Yeah, it's not easy, man. So for the first question here, right? For the first question, hang on. So for the first question here, you would notice that they did say there's a change in temperature. So if there's a change in temperature, then the total uncertainty of that change, right, will be 1 degree Celsius. Okay, but just be careful, right? I'm spotting your working here, right? So not that I'm finding fault, right? Okay, but just be very careful because an absolute uncertainty should be always rounded off to 1SF. So technically, you should be writing 10 plus minus 1 degree Celsius. Huh? Okay, yeah, no, those are good questions. Those are good questions because it tells me that you know we need to cover those things. So the rule is the absolute uncertainty of anything, right, must always be rounded off to 1SF, right? That's the rule, right? So the delta T, right, that you got here. Now change in temperature will be like, you know, the final the delta T will be T final. Like if you want to show if I want to show you the proper working, delta T equals T final minus T initial, right? It'll be 20 minus 10 degrees, right? Sorry, I'm so sorry. Delta T is the uncertainty of T final plus the uncertainty of T initial. Sorry about that. I thought that was the equation itself. So it will be delta T final plus delta T initial because it's just a subtraction addition function, right? So then that means it's 0.5 plus 0.5, right? That becomes plus minus 1 degree Celsius. And absolute uncertainty must always be rounded off to 1SF, right? So it's 1 degree Celsius. Of course, MCQ, right? MCQ, you got it right, that's fine. But now my concern is, let's say it's a paper 3 section A question, they ask you to present the working, you have to present it like that, right? So it's 1 degree Celsius. But they ask you for what's the percentage change. So percentage change will be delta T over T, right? Times 100%, right? So it'll be 1 degree Celsius divided by 10, right? And therefore it'll be 10%, right? 10%, right? There you go, 10%. Like that. Yeah, yeah. Sorry. So let's say I ask you to present delta T, right? I ask you to present delta T as a statement on its own in a section A paper. Then the delta T will be written as 10 plus minus 1 bracket degree Celsius. Yeah. Okay, not 1.0. So 1.0 here, I'm just looking at this working here, and I just want to remind you that that's not quite right. Okay. But that's totally fine, right? Let me see this, right? Because with this I know how to fix whatever you need. All right. So it's totally fine to let me see it. Right, there you go. Okay, cool. Right, let's go. Okay. Um next one, gravitational potential. Do I need to do this? No? No. But this is a bit tricky though. Because if like they ask you for gravitational potential, this will be joules per kg, right? Yeah. So obviously B is out because it doesn't look like joules per kg there, right? And in fact, there's only one other unit with joules, no, with kg, right? If you can remember that gravitational potential units is joules per kg, then D is the answer, right? It can't be B. So there's only one other option with kg in it, right? But that would require you to remember that gravitational potential, the base, I mean the units is joules per kg, right? So of course, then the question will be like, how then do you work done per unit mass, right? Yeah, work done per unit mass. Wait, hold on. Work done per unit mass. Wait, work done per unit mass. Work done per unit mass. Oh, shoots. Oh yeah, you're right. Okay, so this one has kg in it, but then the newtons here. Hey, it's not easy, this paper. Yeah, not easy, yeah. So A is the answer, right? Yeah, A is the answer. If you do this working here, A is the answer. Damn. Okay, cool. Right, that was a bit shocking. Yeah.
Uncertainty is 2S if it's more than 2%.
No, oh no. Huh? Where do you get that from? No. Percentage uncertainty is just 2SF straight up.
Oh.
Yeah. Okay. So the rule is percentage uncertainty doesn't have to be 1SF. Absolute uncertainty absolutely must be 1SF. Okay? Right? Percentage and fractional uncertainty, and fractional uncertainty is not in a fraction. Fractional uncertainty is in a decimal. Right? And they can be 2SF. Yeah, 2SF. That's fine. No one else is here, right? Okay, yeah, that's fine. Yeah. 4? You want me to go through 4? Oh, yes. Okay, can 4. Let's look at this. This is a legit IB question. So the tough part is, okay, so G is in what units? You see, G is in, you wrote 9.81, right? But you didn't write 9.81 meters per second squared, right? So G, the units is in meters per second squared. That's the problem, right? Because down here they say 100 km per hour. So the problem is you need to convert 100 km per hour to meters per second. Yes, which you do you? you tried very hard to. Right? Had a lot of hiccups there. Right. There is a quick conversion though. Km per hour to meters per second. There is a quick conversion, which is what? Do you remember? Yeah, try to remember. 3.6. So just 100 divided by 3.6. That's the conversion. Yeah, that's pretty much it. Okay, but it doesn't really help because you don't have a calculator, right? But what you can do is you can round it off to 4. And it becomes a little bit easier. Then it becomes what? 25, right? So it becomes 25. So you want to accelerate 0 to 25 meters per second in a matter of 3 seconds, right? In a matter of 3 seconds. So then it'll be what? So that will be like 25 minus 0 over 3, right? That's acceleration. That works out to be what? So again, 25 is not really divisible by 3. It's about 8, right? You just write 8 lah. 8. Right? 8. Okay? It's close to 8. Right? Close to 8. And I mean, if you look at it, and they want you to compare it to, like, it's 8 meters per second square, right? And they want you to compare it to G, right? Because they give you the values in G like this. Well, what's the closest one you can get? Yeah, 0.9 of G. Yeah, 0.9 of G. Okay? Right, 0.9 of G. That will be the answer. Eh? The answer is D, meh? Oh, you wrote it the other way. Okay. Sorry. Yeah. Okay. Scare me. Okay, cool. Right, there we go. So that's 0.9 G. Okay, cool. All right, what's the next one?
6.
You want to do 6? 6 is something I've done recently, right? Do you need me to do anything else? Let me know. Yeah. Okay, so do 6, huh? Okay, 6 here. What's the thing to 6? Ayo, your. Ah. Oh wow. Okay. Hey, you established the.
No, I don't know right.
What do you mean by you got it right, but you know how to do? Like you got all your values correct, what? Okay. Let's do this. So this is one of those like questions where oof, it's a little bit more complicated, right? But you need to understand this, huh? I'm pulling the mass on top, right? I'm pulling the mass on top. The mass slides over the trolley. They did say it slides over on the surface of the trolley, right? And what happens is that the trolley will experience, right? Like, since you're dragging the mass on top, the trolley will be dragged along with it, right? Okay, the trolley will drag along with it. Instead of telling you the acceleration of the mass, they tell you the acceleration of the trolley. They say that the trolley accelerates at 1 meters per second squared. So this trolley here, right, this blue thing here, is accelerating at 1 meters per second squared. Okay, with acceleration comes resultant force, right? So we play that game again. Acceleration, right? So we think about resultant force. Okay, hang on. But the pulling force is pulling the 2 kg mass, right? So where's the resultant force acting on this 5 kg mass, right? So the F net, right? Never mind, we just calculate first. F net on the 5 kg mass is equals to MA is equals to 5 times 1, right? Is equals to 5 meters, 5 newtons, right? So the resultant force acting on the trolley is 5 newtons. Then the question is, where is this 5 newtons coming from? They did say that the surface here is smooth, right? They say the frictional force of the trolley on the ground is 0, so it's a smooth floor, right? But where's this force coming from? Where's this 5 Newton force coming from? The 5 Newton force is coming from the 2 kg mass. The 2 kg mass is dragging, right? It's like scraping the top of the trolley, right? Dragging the trolley along, right? So where's the direction of this 5 Newton force by the 2 kg mass? Where's it pointing at? It's pointing to the right. So this is the 5 Newton force as you correctly labeled. But maybe what you should do is this. Maybe you should write out a statement. This 5 Newton force is by what on what? By 2 kg on 5 kg, right? It's by the 2 kg mass on the 5 kg mass. Correct? Okay, good. Then, right, you did draw, right, the force backwards correctly, right? So there is a 5 Newton force acting on the 2 kg mass. Hang on, right, acting on the 2 kg mass like this. There is a 5 Newton force acting on 2 kg mass. But what is this on and what is this by? This one is on the 2 kg mass by the 5 kg trolley, right? Okay, by the 5 kg trolley. This is the action reaction pair, right? So when you look at the 2 kg mass, right, after all that, then you realize that, okay, right, so there is a resultant force acting on the 2 kg mass, right? 8 minus 5 on the 2 kg mass is 3 newtons. But I don't think that's what they're asking for. What they're asking for? Coefficient of dynamic friction between the block and the trolley, right? So they're asking for this 5 Newton force, right? So the friction, right, on the 2 kg block is equals to mu n, right? And rightfully, you already done the mu, the n being the 20 newtons. So the 5 is equals to mu times 20 newtons. And therefore, mu is equals to 0.25. Just no units. Yeah, 0.25. That's it. Oh yeah, they have different acceleration. Yes, you're right. I mean, what is the acceleration of the 2 kg mass? It'll be a bit weird. Yeah. Oh yeah, it's 3 newtons, right? 3 newtons divided by 2 kg mass, yeah, 1.5 meters per second square. Yeah, it's a different acceleration, right? I mean, a while later, the 2 kg mass will slide off the trolley, right? A while later, it'll slide off the trolley. Can? But not that easy either. This question is quite interesting. All right, good. Let's try the next one. This one, number 7. Do you need me to do number 7? No? You okay with number 7? Yeah. Don't worry, yeah. Right. So I don't like I don't judge or anything like that, and nobody judges anyone else as well. But I'm trying to see this myself. Yeah, the guy has to have weight, and the guy has to have normal force, right? Right. So D don't make sense because D don't have normal force, Oh no, sorry, there's a frictional force. Oh, I missed out the frictional force. So there is a frictional force, right? For C. So that's why C makes sense. Sorry. There's the weight, there's the frictional force, and there's the normal force. The frictional force will balance the weight, and the normal force will provide for the centripetal force. Right? D is wrong because it has the frictional force, it has the weight, but there's no normal force. So how does it move in a circle? It needs a normal force to provide for the centripetal force. So D is wrong. B is wrong because this force pointing in, right? You see this force pointing in here, right? This force pointing in is the force that the motorcycle exerts on the wall, but it's not the force that exerts on the motorcycle. It's got nothing to do with the like the motorcycle at all, right? It's like acting on the wall. So B is out, right? A is wrong because even though there's normal force to provide a centripetal force, right? You're completely missing the actual other forces, right? So you cannot not, even though they balance, you cannot not ignore them, right? You cannot ignore them, sorry, right? So it will be there. So C is the answer for this. Right? Cool, 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 cool. Hot damn! Didn't I do this? I did this, right? I mean, I did this and I put in a group chat though, right? Yeah. So for this one, just take note. Okay, I was doing this with my the class just now as well, right? So just take note of this, huh? This motor, this particular question here, right, states that the mass was at rest at first, and then it gains a speed of 4 meters per second after 2 seconds, right? So you have to consider the work done by the motor as what? Consider the work done by the motor as what? KE plus GPE. You have to add in the KE because the motor helped the mass gain KE, and you have to add in the GPE because the mass gains GPE, and then you divide it by the time of 2 seconds. So the working is all over. Right? So just consolidate your working here. Right? So the power of the motor, right, useful power actually, right, is equals to the KE plus the GPE gained by the mass divided by time. Right? That will work out to be half mv squared plus mgh over time. Right? Okay. Now the V, right? The V, some people make this mistake. They think that they need to halve this V. They need to go from 0 to 4, and they feel that they need to halve it so that they can have average KE gain, which is wrong. Okay, because what you want to do is you want to consider how much KE is gained in total. So it has to be the final KE half MV, half M4 squared, right? So don't go and halve it. Then MGH, the H being the height, right? I think the challenge is some students will not be able to know how to find the height, right? But this is my go-to phrase all the time, right? Don't think of all your Suvet equations. If it comes to kinematics and you try to find distance, right? Draw your distance, your speed time graph, right? Then you can find the area under the graph, right? 4 meters per second in 2 seconds. The area here is 4 meters, so the H here is 4 meters, and the T here is 2 seconds, right? You solve it, you will get B as answer. Okay. All right. But let me give you the scenario that I thought and that gave the students just now. So the scenarios I gave them just now, right? The scenarios I gave them just now, right, was this. Motor, right? Motor again, right? Mass like this, right? This mass of 3 kg is being put up at a constant speed, right? Constant speed of 4 meters per second. All right, 4 meters. So side quests are 4 meters per second. And I ask you, what's the useful power, right, of the motor? Right, what's the useful power of the motor? Okay, so in this right, case here, you got to understand that the speed, right, is constant, which means that the KE is constant, which means that the motor doesn't help the mass to gain KE. So you got to understand that in this situation here, right, KE is constant, there is no gain in KE. right? No gain in KE, right? K is constant, no gain in KE. What does that mean? So it means that you do not think for a moment, right, that the motor is helping the mass gain KE. It has already helped it gain KE, right? This is the part where it's moving at constant speed. So the motor's useful power is not to increase KE. So you cannot put KE. So the useful power of the motor is only the GPE divided by the time. So like, the other class, right, the other classes, right, the other students there, some of them are like, oh, I didn't know work done can be considered as GPE, right? Can, right? Work done is energy, energy is work done. Anything to do with energy is just work done. So the gain in GPE by this mass is the work done by the motor. Work done divided by time is the power. Can? Right. So for this case here, but then, some students will, oh, but then, I don't have H and I don't have time. I don't know how to use these values here. So it's just mg h over t. And if you rewrite it, it will be mg times h over t. And therefore it becomes, right, 3 times, I mean, if you're using 10, right, then times 4, right? Because the h over t will be the speed at which it gains the height, right? So it's just 4. So this turns out to be 120 watts. Can? No problem? So I can throw in efficiency. So let's say I throw in efficiency, okay? If I tell you that the efficiency of this, right, the efficiency of this one here is 75% efficiency, right? Let's say that if the motor is only 75% efficient, then my question to you is, what's the input power? How much is the input power, right? Guys, work this out. Let me just use the restroom for just quickly. Okay, done. Right, so what's the input power? So this efficiency 75%, 100 and hang on, so it's 120 divided by 0.75, 160 watts. Okay, right, 160 watts. So I think like I want to bring this up, right? Because I think the concept of efficiency, right, is like, sometimes some people forget. So efficiency is defined as what? Let's say it's a paper 2 question. Like I ask you, define efficiency. How do you define efficiency? Eh. So efficiency, okay. So you got to remember why efficiency is such an important thing, okay? Because efficiency, right, can be asked anywhere in chapter 1, can be asked in chapter 3, can be asked in chapter 8, right? Right, or anything to do with energy and power, right? They can ask it, right? Chapter 2 also, sorry. Okay. So just take note of this, right? So efficiency is useful output over total input, right? So efficiency is useful out over total in, right? So it will take a bit of skill for students to understand what does it mean by useful, right? So if you look at a motor like this and it's pulling this mass up, this crate up, right? Right? So what's considered useful then? The usefulness of it is pulling it up, right? The fact that it gains GPE, that means that it's being pulled up. That's the useful work done, right? But the useful work done doesn't include KE because there's no gain in KE, right? Other than from the other question that we just did, right, from your paper itself, there's a gain in KE for that one, right? So that we consider all these as useful power, right? So if this is, if the useful out is 120, efficiency is 0.75, then the total in will be, right, useful out divided by 0.75, right? That's how we get the total in. Now, I'm saying this because there was this other day, one of the students did mention, right? They thought that the useful, sorry, they thought that this 120 watts is a useful. Then to calculate the input power, if the efficiency is 75%, they thought they had to multiply it by 1.75, right? They thought they had to multiply by 175%, right? So, I mean, it's just an honest mistake, right? So it's totally fine. I'm not going to judge the student for that, right? The point is, right, you got to understand it's not like that. That's why equations and the definitions are super important, right? Um, one thing that I just tested the other class, right? The earlier class, I tested them on something, and it kind of like just reinforced the idea that these things some students will forget, right? Let's say I have a 3 kg mass, and let's say it was initially at 2 meters per second, and it does gain ke, and the final speed is like 7 meters per second, right? And let's say that the k sorry, the final speed here is 7 meters per second. So from 2 meters per second, right, raised up to 7 meters per second. The question is, what is the change in ke? Like, what is the gain in ke? Now, I'm asking you this because I'm setting a trap, right? I want students to, right, make the mistake of, they think that, oh, you want me to find the change in ke? I know that it gains 5 meters per second, so I want to write half m times 5 squared. That is wrong. Right? Remember that is wrong, right? So you cannot take half m times 5 squared. You think that 7 minus 2 is 5, so you want to find, oh, the increase in ke is half m times 5 squared. That is wrong. It has to be half mv squared, right, minus half mu squared. Okay, right? That is the correct way of doing it. Look around for some snacks. Mm-hmm. Hey, you went to school today? You go to school today? Oh, you did? Okay. Okay, there you go. Put it aside. Okay. That's for that work energy power thing. Okay, good. Can I move on? What's the next one? 11. 9 verse. 9 verse is it? Yeah. 11. Wow, that's nuts, man. That's crazy. These people are damn off. Okay, fine. Okay. Seeing this, right, makes me very nervous. Seeing this makes me very nervous because, we know that the particle doesn't, we need to draw the wave, right? We need to draw the shifted wave and all that. Okay, I'll go through this one later. Right, what's this? 9, I need to do 9. Wow, you double circled it. Double circled it, and then so what happens is this, right? You're squishing it until the elastic potential energy stored is 1 joules. Okay, 1 joule. Then I ask you, masses are released. What's the maximum speed reached by mass Y? I don't know whether the 1 joule will be of any help though. Hang on. So what I'll do is that I'll understand that when the spring is compressed, right, the spring will push the two masses away from each other, right? But one thing that I see you're working that you have missed, maybe because they try to distract you by using the word energy, is that whenever you get this sort of like setup, the kind of scenario that should click in your head is actually momentum. Didn't think of momentum, right? But yeah, it's actually, I would think that I would start off from momentum first. Whether or not this energy can be used, I have to think twice, you know. I have to think twice about this. I don't know whether or not I will actually need this moment, this speed. By the way, this 3 kg, this 6 kg, right? So I should understand that the mass x will reach a final speed, mass y will reach a final speed. So it will reach a final speed of Vx and it will reach a final speed of Vy. Okay? Right? And yet the momentum, when we add them up, it will be zero. Right? Don't forget, momentum is directional. So the momentum gain this way, the momentum gain that way, actually add up, the whole system will be zero. So you got your 3Vx equals to 6Vy. Oh, I mean, you written it there. Yeah, there you go. You wrote it there. What? I think one thing that you might miss out is that the Vx over the Vy, right, will be 2. Like, I would rather write it like that instead. They want you to find the maximum speed. I think you almost got it right. Because the next thing you're supposed to do is actually half mvx squared plus half mvy squared is equal to 1 joule. I think that's the case now. I think that will be the case. But it seems very complicated, no? Like very lengthy. So, yeah. But actually, I don't know whether this will be absolutely right. But okay, we'll try. So the half, what, times 3, and you know what, Vx, I'm just going to sub in like 2Vy, right? Because ultimately they want me to find Vy, right? Plus half times the 6 times Vy squared equals to 1. Am I going to get in trouble here? I hope not. Looks like I can factorize the whole thing. I can like kind of like find Vy here. Right? So 3 over 2 times 4. 3 over 2 times 4, what's that? 12 over 2, 6. 6 Vy squared. Right? 6 Vy squared. Plus 3 Vy squared. Oh, looks like a nice number now. So 9 Vy squared, right? So the Vy squared is 1 over 9. And therefore the Vy is 1 over 3. Which is 0.33 meters per second. Wow, not easy. And I can understand why you spend so much time on the first few questions. Because like this kind of like really tedious, right? So but you have to learn how to work fast, so that's the thing. Okay, but, I mean, chances are the actual exam itself is not going to be like, you know, that tedious. But obviously your teachers have chosen a set of questions that are all the tedious ones. Like they probably have like a collection, these are the tedious ones, right? So we just chuck it all full of the tedious questions. It's damn tedious, what? Look at that, all the questions so far I've done so far is all very tedious. All right, 9 done. 10, do I need to do 10? Again, I'm a bit, I'm just a bit like, you know, nervous when I see like, you know, students draw the arrows pointing this side and that side. But I guess in a way you understand that positive displacement means to the right. So all the particles has moved to the right, right? And on positive, this one here. So A is a compression, right? So this one here, like I've done this in class quite a number of times. 11, G. V. Louise. All right. So for 11, we have a frequency of 500 hertz. Closest distance between 2 points on the wave that has a phase difference of 60 degrees is 0.05 meters. So you know you gotta have to draw a wave like that, right? One wave, which you have done, right? Which you have done. So the idea here is this, but strangely enough, I don't know why you chose all the weird values there. 60 degrees is what? 60 degrees is from, well, I mean, you are almost right. I think you almost got it right. Okay, from here to here, right? Isn't that like 60 degrees? Okay, right. You understand why that is that 60 degrees? I mean, the whole thing is 2 pi, right? So 60 is some here, like, lesser than 90, that's fine, right? But 60 degrees is what? It's 1/6 of the entire wave. Isn't it? 60 is 1/6 of 360, right? So you almost got it right because the distance between these 2 points, the distance between these 2 points on the wave, right? And we are talking about distance, we're talking about horizontal distance is 0.05, right? So what is the entire wavelength? What's the entire wavelength? 0.05 times 6. Yeah, so lambda is equal to 0.05 times 6, which happens to be 0.3 meters. And the frequency is 500, speed of the wave v equals f lambda. Right, so 500 times 0.3. Still not a very nice number. What the heck is that? Is 150? Yeah, 150. Yeah, 150. So C is the answer. Okay, can? Alright, so I mean, it is tricky, so you have to draw it out to visualize it. If you don't draw it out, it's very hard to, right? But it's a good thing that you visualize it. Did you get 150? Oh yeah, you did. Alright, you did. Okay, so that's for 11. 12. 12. Huh, what? 12, huh? 12, huh? 12. 12, 12, 12, 12, 12. Okay, disclaimer. So 12, right, is one of those questions that I recall myself. And the annoying thing is, how are you supposed to know this, right? So what happens is that, how are you supposed to know that when you double the slit width, that means you increase the size of the slits. How are you supposed to know that from intensity of I naught, it becomes, what, 4 times the intensity? Is that the answer? Oh, it's, yeah. How do you know which one is it? You get what I'm saying? Right? Like in my mind, I would think of two, right? I would think of two. So yeah. Then of course the question is, why is it not 4? Or when would it be 4? Yeah. So when would it be 4, right? So let's address that one first. Like when is double slit and each of them is one intensity I naught. When it's double slit, right? And each of them is I naught, and this one is I naught, and it reaches the middle of the screen here, right? The total intensity at the bright central maxima is 4 times the I naught. Do you remember why? Do you remember why? Because it's amplitude plus amplitude, right? So the bright central fringe is 2 times the amplitude. The amplitude is 2 times, but intensity is amplitude squared, so it becomes 4 times the intensity, right? So for these two options here, it's not correct, because if it's just one single slit and you double the slit, then the intensity is double. Okay, right? Then the problem is this angular position of the first minimum. So theta is equal to lambda over, what's this?
This is
Oh, fine. Okay, lambda over x. Well, that's confusing. So that's a slit width, right? Slit width. Then they say they double the width. So if you double the width, then the theta is half, right? Then let's just be ah.
I think it's a million dollars.
Oh no, so my point is that we go by elimination.
Oh,
It's not 4i naught. Because we know that the 4i naught case is when it's double slit. When there are two slits, two sources. This is just your one single slit, right? Increasing in size by 2 times. Like it becomes 2x, right? So you got so why is it not 4? I'm guessing is because
I asked my teacher.
actually yeah.
Like, he asked,
Yeah.
and he drew the graph.
Uh-huh.
He said what's then he said the light wave has the same energy.
It has the same amplitude.
He said same energy and same
Okay.
the graph like that. higher or but
Yeah, correct. Yeah. It does become narrower. Yeah, it does become narrower.
is it higher?
Yes, it becomes higher.
Yeah, this is the area under the thing is like the same under both.
Oh,
That's why
the
it
area under it. I never thought of that before. I don't think he's wrong, but it's never been really thought before. You get what I'm saying?
oh,
I don't think he's wrong, right? He is not wrong, right? So he's saying that the pattern went from like that to like this, right? Correct? Yeah. So I'm what I'm saying is that I don't think he's wrong, but it's just that it's not something that we regularly teach. Like we don't go around teaching that, oh, the area must be the same, which is probably why this kind of like this question is like kind of lost on us, like even including me also. Yeah.
he used that to explain why the peak is down.
No, I think for me, right? For me it's more like if the slit is doubled, the peak will increase. I know that, but I don't know how high it will go. Will it go to 2 times or 4 times? So mine is by elimination. I know that it can't go to 4 times because the 4 times one is for double slit, right? For this one here, it's like, if it's not 4 times, then it has to be 2 times. Also, I'll choose B the answer lah, based on that. But knowing that it becomes okay, so Ruben, knowing that this thing here becomes narrower, right? Like by half, I don't understand how, like, because it's a curve, right? Right. I don't see how you would be able to predict that the peak will become, yeah, become like, 2I know, unless you approximate it to a triangle. That means if you tell me that there's a triangle with this base at first, right? That means base B, and then you have another triangle with half base B, right? Half of base B. Then you tell me that, oh, that because of that, then the height is 2 times the height. Then yeah, I can understand that. Yeah, that one. I mean, if you talk about it in terms of like area under the triangle, yeah, that's fine. And but usually even your teachers as well, when they're teaching this topic, they probably wouldn't have mentioned it, right? It's kind of like more like a afterthought that once you do the question, then we realize, oh yeah, it's based on the area. Okay, next one, come. Do I need to do 13? 13? 13, huh? So they did indicate that the first slide is unpolarized, right? So the first one is unpolarized. So the first part of the question already sets the tone, right? So read the question carefully. This unpolarized light. So which means that this I naught here, right? Intensity here is for unpolarized light. It's unpolarized. Okay? But if it's unpolarized, right? If it's unpolarized, then what happens to the intensity after passing through the first polarizer? What happens to the intensity after passing through the first one? Yeah, it's always 50%. So no matter what angle x is, right? That means if I can rotate angle x by 180 degrees, it doesn't change this intensity. It's still gonna be 0.5 times the intensity. Okay, right? Did they say that x and y are parallel at first? Did they tell you that x is parallel to y at first? Did they say that? Did they explicitly say that? Explicitly, they didn't say that, right? But yeah, they did say that they're arranged so that the light emerging from Y has the maximum intensity. So at the start, what was the start of the output? Like, at the start when theta was zero, when theta is zero, what was the intensity from Y? It would have been, what's the intensity of Y? Yeah, no, yeah, it will be just half of this one, right? So whatever came from X, right, passes through Y if they're parallel to each other. At the start, it would have been 0.5, I know. Now, do you agree that that's the maximum, that's the maximum intensity that you can get out from Y? Right? Can, right? Okay, good. So they did say, what is the first three successive values of theta for which the final transmitted is a maximum? So I would expect that the first answer, that theta is zero. Yeah, right? For one of the answers, theta is zero. So is that theta equals to zero there? Don't have, right? Don't have, right? So if it's not zero, then 90 can't work. So A and B sure will be out, because if Y is 90 degrees to X, right, you're not going to get anything. right? So what do you have now? Right, either C or D, right? So C or D, geez. Doesn't it all look possible? Oh yeah. 180, 360, that sounds okay. What's 540 though? 540 is how many rounds? 1.5. So one and a half, like it's like half turn, and half turn, is it? So that means vertical, turn, half vertical, turn and a half still vertical. So this is vertical, vertical, vertical. Alright, that so C is possible, right? But what about this though? Huh? It's also possible. What the heck? Dude, what in the damn hell? What? What the? That is damn dumb lah. That's damn dumb. What kind of stupid question is this? This is not physics. This is Mensa. This is not Mensa. This is just APGP math shit. That's so annoying. I'm sorry. It's just sometimes yeah, your teachers annoy the hell out of me. Like, I just cannot take it. Okay, now mind, we will do better. Next one, what's the next one? This one okay? This one okay, yeah? Alright, next one. You want me to go through this one? Huh? You okay also? Oh, don't need, ah? Okay, next one. This one also don't need. Come, tell me which one. Come. Shit. Okay. Uh, so this is not Earth. Alright, this is not Earth. Okay, it's not Earth. Alright, let's see. So the planet has an albedo of 0.3. I'm gonna ask you this, okay? What does okay, so let's try to understand some symbolism here. Look at this arrow. Boom. It's like it don't care about the atmosphere. No shit given to the atmosphere at all. Right? So what does that mean? Why? Why does the incoming intensity not have anything or any interaction with the atmosphere? Yeah. Okay, couple of reasons, right? So this is some random planet, right? I don't know, right? Maybe the atmosphere is just made out of some gas that doesn't interact with the incoming solar radiation. Okay, in fact, I'm gonna ask you this, okay? What's the main type of solar radiation? What's the peak type of radiation that we get from our sun? Yeah, visible light. We actually get visible light, and the Earth is absorbing that visible light. So you got to understand, absorbing visible light actually helps the Earth to gain energy. Yeah, it actually gains heat from visible light. I know it sounds impossible. It's not like, oh, I stand there, right, I'm gonna get like heated up by the like by light, right? I shine a torchlight and you're gonna get heated up, right? So obviously a torchlight is nothing, right? But the amount of visible light that the sun produces when our skin absorbs that photons, we actually do gain some heat from it, right? So there is always some sort of heating effect from absorbing radiation. Okay, so it's got nothing to do with the atmosphere, right? So of this 100, albedo is 0.3, right? So 0.3 is reflected. So how much does it absorb? Yeah, so the amount of absorbed, right? The amount that's absorbed is 70, right? Is 70. Okay, the amount absorbed is 70, right? Yeah. So there is one problem with this picture, and the idea here is, right? The idea here is, so the amount that's being radiated is 70 from the surface is 70, right? From 70, right? Okay, FOR. But when you emit out the 70, some of which is being absorbed by the atmosphere and re-radiated back inside. So if you look at it, actually the total that the surface receive is 70 plus 60. Did you get what I mean? Like inclusive of the atmosphere's re-radiation. So in fact, that means that the Earth must try to radiate both out, right? It looks like it's like a cyclical thing. It looks like it's like, oh, what is this cyclical logic thing? Like I radiate back in, I radiate out. Yeah, but that's it. That's what it is, right? That's what greenhouse gas is doing, right? Okay. So in fact, the total here is 130. Okay. So once you discount that atmospheric part, like how much does it come out in total? That's 70. Like this, only this arrow 70, not this whole thing, right? This is wrong. Yeah. No, I get it. I get it. In fact, I have to do this with the rest of them, right? Because confirm they will all ask this question also, right? But then some students will be like, doesn't it mean that the Earth is radiating out 130, which makes no sense because it feels like you're only receiving 100 from the sun, right? How is it possible that it's emitting 130? Right? So it's not emitting, like ultimately it is lesser than this, but right on the surface, it's emitting both the greenhouse radiation and the main radiation itself. Right? So it's 60 plus 70. Right? So the 70 comes out. Okay? But let's do some energy accounting. At the end of the day, how much comes in? 100. How much goes out into space? 30, 70. Still the same, still balanced, right? Okay, it's just that right on the surface you have to include the atmospheric greenhouse gas effect. Okay, okay, yeah. So I don't know what's the answer. 130 lah, right? 130. So D is the answer. Okay, good. What's the next one? Eighteen, 19, 18, 18. You want 19? Okay lah, yeah. 18 is just strictly PV equals nRT, right? PV equals nRT. Then you check how does the N change for the increase in the volume of gas into it, right? So PV equals nRT. Just check the N, okay? All right, let's go through 19. 19, 19. Stupid question. What, yes? Oh, yeah. Oh, careful though. Yeah.
Small n times r equals to 3n times t.
Oh, yeah, that's right. Yeah, you're right.
But t and r are constants.
Two different constants. Yeah, that's right. The only difference between the two constants is Avogadro's number. Yeah, that's right. That's right. Yeah, that's right. But yeah, okay. I mean, just work with the small n, right? So I mean, you're right to put an n2 there. That's fine, right? So kind of like, right, try to figure this out, try how to work it out, right? So it's actually more of math than anything because once you know it's PV equals nRTs, like the rest of it is just math. This one, this is a very silly question. So basically, they just want you to find the harmonics where there is a note in the middle. Like they want you to go and count, like they want you to just like come up with some APGP thing, so annoying, where the note is in the middle. Okay, right? Where the note is in the middle like this. Okay, there's a note there. So they say that give the frequency that have a note at the center of the string. So first harmonic, does it have a note? Don't have. Second harmonic got. Third harmonic have or not? Third harmonic don't have, right? Fourth harmonic got or not? Fourth harmonic got. Fourth harmonic means four halves, right? Four halves means it's like four halves means what? Two ways, right? So it's one and then two, like that. Then this will be the fourth harmonic, right? Then you realize that fifth harmonic don't have, sixth harmonic have, seventh harmonic don't have, eighth harmonic have, all the even numbers. Can? All the even numbers. But then the worst thing is they want you to they tell you that the second harmonic is frequency F. Second harmonic. So how do you go from the second to the fourth? Times 2. Then how do you go from the second to the eighth? Times 2, right? Times 4, right? So if n is the integer and the f is the second harmonic frequency, then the next one will be just what? I think the answer is B. Wait, hold on, let me think first. Yeah lah. So 1, okay, when n is 1, right? So the answer here is n equals to 1, right? The harmonic is the second harmonic, right? Then when n equals to 2, which is the fourth harmonic, right? Yeah, there you go. N equals to 3, sixth harmonic. So yeah, there you go. Annoying question. Okay? Yeah. It's very confusing. It's not even physics anymore. It's like if you ask me about the physics, I know the second, the fourth, the sixth, the eighth, all the even number harmonics have a note in the middle, right? But then you go and ask me to go and come up with some APGP like relationship for, yeah. Okay, never mind. Let's go on. 20 is a commonly asked question. 20 is a commonly asked question. Shall I go through 20? 20, okay. 20, okay. Okay. 20 can be a 2-second question. 2-second. Okay, let me show you why is it 2-second. First part, they say standing wave. Then they ask you phase difference. Okay, between 2 points on the wave, right? Standing wave, there's only 2 kinds of phase difference. It's either you're out of phase or you're in phase. Correct? Look at the options. You only got one option only. They could have made it a bit harder by changing one of the options to 0 radians. Then you'll be like, shit, I have to go and check this. Right? But because they didn't, right? So immediately you can just put C as answer and then you can walk away from it. Right? Yeah, no, really. Sometimes you gotta learn how to pick your battles. Don't try to, like, sometimes you know the underlying thing is that it's either 0 or pi radians, right? As a possible option. Then you see there's only one option, you just choose it and then you just walk on. Right? That guess is even stronger than that's an even bigger strength than having to try to work it out and then try to find answer and then just for the sake of proving it to yourself that you can find answer. Don't need get answer only, move on. But let's work it out lah. All right, it's a third harmonic standing wave. Damn. Okay, you went to draw all the harmonics. Okay, third harmonic means 1.5 waves. Okay, all right. And the distance is 0.8 meters. 0.8 meters, right? But then the 2 points that are separated by the distance of 0.6, right? The trick is this 0.6 meters can be anywhere along this 0.8. Like it can be like from like from the start, right, to somewhere 0.6. 0.6 is where 0.6 will be like 0.6 over 0.8 is how much? Isn't this 3/4? Yeah, 3/4 of the wave, right? So it will be 3/4 of this third harmonic wave, right? 3/4, 3/4. This is 2/3, right? This is 2/3. Which one's bigger, 3/4 or 2/3? 2/3 is 67%, right? 3/4 75%, right? Is this 3/4? This is 3/4, right? That's a bit strange, Then if it's 3/4, wouldn't it stretch to over here?
Oh no, just the wavelength.
Shoots.
It's just 1.2.
Yeah. Made a mistake there. Sorry, 1.2 meters. The whole thing, yeah. So the whole thing is 1.2 meters. So 0.6 is actually half, right? Half of the entire wave, right? Half the entire wave. Okay, so you won't compare nodes to nodes, right? Because nodes has no phase, right? So let's say you take it just slightly out of the node here like this, right? Half of this whole thing, right? Half of this whole thing will be definite, yeah, will be less than 2/3 of it, right? Like half of it will be less than 2/3 of it. So it's like you're always stuck between the top one versus the bottom one or the bottom one versus the top one. Like no matter where you shift this thing side to side like that. Okay? So you will always get something that's on top and something that's on the bottom on both sides of the 0.6, right? And therefore it's pi radians, right? That's the idea, right? So, but one of the most important things is that students always forget that, oh, the phase difference thing, right? So you got to remember that. You see this top part here? That's the top half of the standing wave, right? What is it in phase to? The other top half, right? Right? Like these two purple sides have the same phase. They have the same phase. Do you understand that even the particles, right? Even the particles on it, Jaden, even the particles on this thing here, right? Like individual particles, like all of them have the same phase, like within themselves like that. Like if let's say I compare to like this particle here to another particle on the side here, like that, they have the same phase because they move together, but they don't have the same amplitude. Right? Do you understand that? It's like, you know, they have different amplitudes. One is the antinode, one is this one, right? But they all move together down and up, down and up. So they have the same phase, right? So for standing wave, right, actually there's only two kinds of phase difference. Either you're same phase, which means 0 radians, or you're completely out of phase, which is pi radians. So the comparing the top and the bottom one, right? Then the bottom one will be the other phase, right? Yeah, the bottom one will be the other phase. Like that. Okay, can Okay, good. Right.
What is the particle?
Yeah. So we don't compare nodes. Yeah, we don't compare nodes, right? For phase difference because the nodes are not moving. Yeah. Oh yeah, you are right, right? So it's a good thing they wrote it down there, 0 or pi. Okay, good. What's the next one? Huh? Polarizer again? Hey, hello. Move on already lah. Why? I thought already got one polarizer question already. Do I need to do this? Do you want me to do this? No, okay. 22? 22? Huh? No need? Okay, 22 don't need. 23? Why all these questions coming out as MCQ? 23? Huh? What's the correct answer? C. But you put D. No. You put C. You put C also. So don't need to go through this one. Alright, 23 don't need. Next one. Oh. 24 will be just you have to use the equation from a data booklet. Yeah. Do you need me to go through this? Don't need, 24 don't need. 25? Okay, tell me which one. Tell me which one next. Just choose the next one. You need a 29. How about you? He needs a 29. 29? Okay. 26 only, 26 only. 27. Oh, I mean, careful, 27. Do you know what to do for 27? 27? 27, 27, never find a gradient. Right? If you want to find resistance, never find a gradient. Never base it on gradient. Always go by. Yeah, go by the ratio. So you take whatever V you divide it by the I. Right? So you see, right? Let me ask you this, okay? Between S and T, right? When's the point where they have the same resistance? When's the point where they have the same resistance? At the point where they cross, right? Okay, because that's when the V, right, divided by the I is the same, right? Okay. Then the next thing will be so they did what are they asking for? Shit. What? Really? What? Dang it. So they say that when they are placed in the circuit below, the reading of the ammeter is 6 amperes, which is a combined current from both S and T, but you don't know what's the EMF of the battery. You have no idea how many volts is this, right? You have no idea how many volts is this. Yeah. If you remember me doing this chapter, it was actually a little bit tough. What you're supposed to do is you're supposed to take a ruler, right, and place it on the graph. You have to choose which direction you want to place it. You want to place it horizontally or you want to place it vertically. Like you have to choose. Like, would you put it vertically or would you put it horizontally like this? Okay, since they're in parallel, right? Since they're in parallel, what do they have the same of? They have the same voltage, right? So what you want to do is you want to place it vertically, right? Because when you place it vertically, you are making them have the same voltage. Let's say, for example, put it at 3 here like this. Then that means S gets 3 volts and T gets 3 volts. You know what I'm saying? Right. So when you go back and forth like this, you realize that at this point, when both of them get 4 volts, both of them has 3 amperes, right? Based on this like, you know, you using this ruler here. Both of them have 3 amperes. And because both of them have 3 amperes, right? When you take this 3 amperes here, 3 amperes here, then the total current is 6 amperes. So that's the correct answer. The voltage is 4. Okay? Not 8 volts, not 8 volts. Because don't forget they're in parallel, right? So if this one gets 4 volts and the other one gets 4 volts, in parallel, the EMF is 4 volts also. Right? You got that, right? Okay, cool. Okay. So then the next thing is I kind of like just want to make sure that you understand this. Like sometimes they may even ask you, okay, this one doesn't look too nice, the graph. Yeah, the graph doesn't look too nice. But you know, if let's say they say that, you know, I placed it in series, and therefore in series they must have the same current. And for them to have the same current, you have to put your ruler like this. You put it horizontally, and then you need to match up, right? Until the point whereby both their voltages add up to the EMF of the battery. I don't know whether you remember me doing this. Like this was quite a long time ago. Huh? What the heck? Are you serious? Yeah lah, that means you have to put the ruler thing. I didn't do that for the revision. I didn't do this ruler thing for the revision. How many things do I have to go through? I must go through so many things, man. Okay, right. I have so little time left. Okay. But just remember that thing. So if it happens in paper 2, then it happens in paper 2. Okay, anything else come? Was that 29? 29. Okay, make sure you know how to do this. V over D is the electric field inside the two plates. The charged particle experience a force F. F equals to QE. Right? F equals to QE. What's the charge of the particle? You make Q the subject. Right? So there you go. Okay, so that one's correct. 29. This is variation of distance R with a V potential from a charge Q. Okay, hang on. All right, what is this? Right, again, layman's term. If I ask you to describe it to a friend, right, what is this? Mm, layman's term, layman's term. Yeah, it's just voltage. So basically you have a Q here, right? You have a charge here, a spherical charge, right? And based on the graph, there's a voltage on the edge of right on the surface of the charge. And as you go further and further away, right, the voltage decreases, right? So the voltage decreases according to this graph here, right? You can see the voltage decreases like that, right? And the reason why the graph looks like this is because V equals to KQ over R no square. When do you use the square? Then you know this, then why you go and write that? Field strength. So they want the field strength as distance S, is it? They want field strength. Then it's just a tangent, Yeah. Oh, wait. There's another option here, is it? Damn it. Yeah, the answer is D. It's the negative. So, okay, so one of those small things I said just don't bother with, but then it's there. Okay, when I was teaching this topic, right, because everyone's always very concerned about the negative sign, right? But yes, the proper definition of it is that it is the negative of the gradient. So D's answer. Yeah, D's answer is super annoying. So potential, okay, just write this down, right, for yourself and for the final IB exam. Potential gradient, right? Potential gradient equals to negative of field strength, right? Okay, which also means that field strength is the negative of the potential gradient. Annoying, very annoying, annoying. Okay, come. All right, next one, please. What's that? 33. Both of you asking for 33. This is what? This is a full wave rectified. Oh, there's no current. Oh yeah, short circuit, dude. Yeah, what the heck? Short circuit. Yeah, 30 is a short circuit. 31, no need, 32. 32, I went through this in class, right? C is the answer, right? 33, E. 33, why? Oh, because you all never do this fast enough. Yeah, no, damn hard this one. Okay, what do you have to do first? You have to sum these two up first. First step, sum up the two capacitance here. In parallel is what? Good. Bad color. Yeah, C parallel is what? 2C, right? So together, this is 2C. This guy is C. Right? Right. So then the thing is this, before you do any further, you must understand that the charge in this and the charge in this combined one is the same. You had to memorize that.
The charge in 2C is the same as the charge.
The total charge of this combined capacitor is the same amount of charge as C. Right? Why? Because they're in series. And you're supposed to memorize it. It's in my notes. And it's also something that I went through very briefly during the topic 11 revision. So please remember that series capacitors have the same amount of charge, even though they are of different capacitance. So if, let's say, for example, right, even if you have a row of them like that, right? Let's say this is C, let's say this is 2C, and this is 3C. By the time you charge it up, all of them have the same Q. Like Q, Q, Q. They have the same amount of Q. Okay? But then in parallel, the charge is shared. So while this one is Q, then this one and this one, each of them is half Q. Yes, it's only evenly shared if they have the same capacitance. Right? Otherwise, you have to work it out. Okay? Based on that, let's see what's the options. Ah, damn it, what? Where's Z? Z's out there. No, but then B is saying that X has 2 times that of Z. That can't be true. Right? See the 2CV over 3, this one CV over 3, right? So X can't have twice as more than Z. It's half of Z. So the way I look at it, only C is answer. Yeah. Even without bothering with the 2 or the over 3, like, because there's no other option that give me that X is half of Z. So C is the answer. If you have to go and find out, okay, if you go and find out really what the true answer is, right? If you want to go and find out what the true answer is, then you have to go through the trouble of finding out what's the total capacitance of C and 2C in series. So in series is what? What's the total capacitance in series? It will be 1 over C plus 1 over 2C, then to the power minus 1, lecce. Okay, you got it, Okay, next one. 34. Wow, shit. Huh? Wow. So it looks like uranium 237 become 233. So at the end of the day, it's just a -4, right? Okay? It is a -4, but yet the element still stays the same. The element still stays the same. That's the key clue. Yo, this kind of really Mensa question there. Okay, uranium 237. If you alpha decay, right, what will happen? The element will change. Like it becomes something else, you know. You know what I'm saying? The element will change, you know. I think I know which one is this. Either A or B now. Yeah, it's either A. So the element completely changes it. Because the whatever the value is, let's say you don't know, oh sorry, you don't know what the Z value is, okay? Let's say you're not supposed to memorize any of the Z values in it. Right? The Z value here is -2. You have to somehow make sure that it goes back to Z, but the 233 still remains the same. I mean, it's just beta lah now. Okay? So you have to ask yourself which beta decay will give you back protons. Because now you -2 protons. You have to make it go back to 233, Z -1, and then you make it go back one more time to 233, back to Z again, and it becomes the last one becomes uranium again. It's not about the sequence. It's just a combination of decays. So we know that this is alpha decay, right? Then what will get you one more proton? Isn't it? That means you want it. Oh, that means there's too many neutrons, right? Too many neutrons, the one neutron become a proton, but the mass number still stays the same. Then another one neutron becomes a proton, but the mass number still stays the same, right? That's a beta minus, right? Beta minus, right? So this beta minus and this also beta minus, right? So unfortunately, that one you have to go and memorize. You have to go and memorize which decay will add on one more proton when it decays. Yeah, right. So beta. So you look for the option where they have one alpha and two beta minuses. There's only one option, so B is the answer, right? Yeah, it cannot be C or D, even though it looks like, oh, I don't know which is the correct order, right? Yeah, it can't be that, right? Yeah. So the understanding is B in whichever order. It could be alpha first, then beta minus, or it could be beta minus, then alpha. It doesn't matter. You still get it. I mean, you fulfill whatever the question wants. Yeah.
T minus 1 is not X, right? It becomes Y.
Yeah, it becomes something else. Yeah, that's right. It's just another element again, right? So it becomes like yeah, okay, why? Right? So it becomes something else. Yeah, you're right. Okay, next one. Okay. 情况啊。哦哟 increasing wavelength. So you got two low energy. This is an A level question. You got not IB question. You got two low level. You got two low energy level photons being emitted. That means you will only. That means and it's drastically different from that. That means of all the options that you choose from you must have exactly two very low energy and only two low energy photons, right? So that means this only two very low energy transitions, right? Like distinctly low from the others, right? A is your answer. Because you see this transition here and this transition here, right? It gives you that two very low energy transitions. But let's draw the others. Let's test out the other transitions. Okay, what are the other transitions? From 4 to 1, from 3 to 1, from 3 to 2, from 4 to 2, right? These are high energy transitions, right? And they should be all quite close to each other because if let's say you use the length as a scale, right, of how much energy it transits, right? you will see that all four of them are very close to each other. So they represent these four. Yeah. And there's no other versions, right? There's no other low versions of it, right? So like, A. As strange as the energy levels looks, but it's just A.
I thought like the bottom two lines
It's not. So these are energy levels. Don't confuse it with the photon energy that are being emitted. The transition, the amount transited represents the energy of the photon, right? So it's about the gap size. The gap size, right, represents the energy of the photon. So for this case here, right, the gap size here, this one here, and this one here is the one there. The gap size. Okay? Okay? Why won't you think so? It is possible.
it's four lines
Hmm? The transitions are representing these four photons. So the emission spectrum is basically what is being emitted, right? Energy packets that are emitted, right? Each one of these transitions is an energy packet. So these four transitions have very similar energy levels, which is high energy level because they're high frequency, right? But they are quite close to each other.
so the small gaps
Yes, yeah, that's what I'm trying to show you. I'm trying to show you this one. Then you see, I'm trying to show you this one. The transition here, right, represents the photon here. Then this one here represents the photon there. No, 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 no. No, don't mix it up. Huh? The gap here represents the photon here, like the photon here. The gap here doesn't represent the gap here. The gap here, this gap here represents one of the lines. This other gap represents the other line. Like the line itself, like this is the photon that's being emitted itself. This is the energy that's being emitted itself. Yes, correct. The line is the energy of the photon itself. Okay, Okay, that's for 35. Nah, not easy, not easy. 36. 36 only, both. Okay, 37. 37. Dio?
what's it not
Because it's per unit time. Decay constant always got time limit one. Whenever I was teaching topic 12, whenever I say decay constant, I always say that decay constant is the probability of decay in the next unit time, right? So lambda always has a time factor, and lambda is never ever, right? Lambda is never ever like it's not based on like seconds. It can be anything. It can be lambda is like, let's say 0.5 per year also can. That means the chance of decay is 50% in 1 year, right? Lambda always has a time constant, has a time, right, factor to it. 37, right? 30, shit lah, 30 is nature of science. Paradigm shift. You want paradigm shift? Paradigm shift. Paradigm shift. Paradigm shift. Paradigm shift. I would say D is the answer. Why is it not A? Because not big enough. It's not big enough impact. Like you got to think about what was a big impact. That's why I do sometimes, sometimes I do like talk about like what was a big impact in the like I try to give you a bit of stories, right? So equivalence of mass energy. I told you what was that? I told you that Einstein was a guy who came up with this, right? Equivalence of mass energy, E equals mc squared, right? But he didn't win the Nobel Prize for this, right? Right? Because it was used to make an atomic bomb, that kind of thing. Yeah, I mean these like more like ground shaking. It's like one of those ground shaking discoveries. Rutherford yeah, actually, yeah, I would think so. Rutherford Gold experiment was a paradigm shift because they did not have an idea of what the model was. Someone had an idea, but his idea was wrong, right? And then for many years they just kind of followed that guy's wrong idea, the plum pudding model, right? Then Rutherford came out with this model and then basically just dissed the guy lah, right? I think the guy was dead already by then, so you didn't have to worry. But you know, scientists are funny one lah. Like you say something right, then another living scientist say that I think you're wrong, right? Wow, then they fight lor. Yeah, like Edison and Tesla, right? Wait, what's this? Ah, this one is the graph itself, right? Yeah, the graph itself. But it looks like what's the difference between
Like the region.
Wait, you guys are like making me like confused. Huh? Oh, the shaded unshaded region. Oh, but why does my this one here after you like it looks like they added and like the scan added another line also. Oh no, there is a line here. This one here should not have a line. Should not have a line. Oh, what the freak? Wait, what does it say? Line of stable nuclei and the shaded region where the unstable nuclei beta minus. Beta minus is what? Too many neutrons. Yeah, too many neutrons. So these answer. Yeah, 40 is B lah. 40 is B. Yeah, 40 is B. But what was the experiment I quoted inside my notes? For wave nature of electron. Yeah, I know lah, but fire the electrons at what? Yeah, powdered graphite, right? So basically they were doing electron diffraction on powdered graphite. It's just that this thing here they give you a different scenario. They ask you like, oh, like, so which one is the proof, right? It's actually electron diffraction from crystals. So B is the answer. So, correct. Then they down here they're using crystals to diffract.
A is just showing the neutrino came out with the electron.
What?
Option A is showing that the existence of a neutrino or anti-neutrino.
Yes. Okay. So A represents as an anti-neutrino. Existence of atomic energy levels. C. What's the evidence for that?
The emission or the absorption.
Is emission and absorption spectrums good? Existence of nuclear energy levels for D? The decay itself. Yeah, the decay itself. Yeah. Okay. Paper 2. Oh, shit. Can. Never mind. Let's go. Paper 2. Alright, paper 2. Is there any particular questions you want me to go through? I mean, we are running out of time, but usually paper 1 is more problematic. Paper 2, do you have anything that you feel like is a bit of a question 3?
Oh, yeah.
Yeah, I was looking at question 3 also. I was wondering what in the world is going on. What do they want? Yeah, it is, right? Just because of that one topic and then revise, then you all cannot make it. Why ah? Why ah? I have to revise everything, you know. I'm tired. No, I'm just kidding. Of course, I'm supposed to do that. That's my job. Topic 8. So I mean the solar radiation is 680 watts per meter square. So every meter square of the solar cell can absorb 680. But then the roof tiles have albedo, so it will reflect 20% away, right? So 20%, so what is the amount that is actually absorbed? Okay. Okay, so technically albedo and emissivity actually should add up one. This one here a bit wrong. Like albedo and emissivity should add up to 1. Yeah, so I think so. Because it is in the new IB syllabus, like the new textbook says like, you know, E plus alpha is 1. Yeah. Anyway, never mind. Ah,
Yeah, yeah. So for the first part, I'm a bit confused.
uh-huh.
First, you calculate the heat energy. Then you find the useful power.
So basically you need to raise the temperature of the water from what? 15 to 30, right? 15 to 30. So you need this amount of energy, like what you calculated, 250 kilograms of water, right? 15 to 30, right? So the amount of power that you need is what?
437.
Okay, so that's what you have done, is it?
Yeah, but then
Uh-huh.
as an albedo, right, does it mean that you need to, then this is 70%. The useful power is 70%. So you need more to be incident.
Yeah, you do lah. They didn't mark you down on that.
No, it's correct. I was just unsure whether I could just work with the 0.75 or if I had albedo.
Actually, a lot of things that seem to be missing. No, you're not wrong, eh? How come you don't have to? Yeah, it's very confusing, eh? How come why is this like a lot of things missing? It feels like there's a lot of things missing, you know. So number one, this is the total energy required to heat up your water, right? Um, like okay, then let's talk about it per. Right, so if you want to heat up all this amount of water in 1 hour, so you need to take this, and this is the power required, 4375. This is the heating power required. Efficiency of the heating system means that you need to divide it by 0.3. So this is the total amount of heating efficiency, right? Yeah, so this is the total amount of power required, right, on the solar panel, right? So 14,583. But then yet, right, then you say that then actually it's a bit weird because we need to consider the albedo, right? So it's actually 80%, right? So like this is 80%, right? Yeah, this is the amount that needs to be absorbed. So you need to take this value divided by 0.8.
I think the answer is wrong.
Then only after that, then you can, yeah, your answer is wrong. Yeah,
So this one
your answer
is
is wrong. So
then you divide.
yeah, so this value here, the 14583, you're supposed to divide by 0.8 first, right? This will give you the total power needed, right? From the sun, right? From the sun. The sun you need to provide more power because 20% of the sun's power will be reflected away, right? Then the minimum area will be this one divided by 680, then you can get this one. Yeah. So I think you're missing the albedo part. Yeah. The teacher also. Okay. What's the next one?
Part 2.
Part 2. The temperature, is it? Oh, okay. So you said 680, is it?
Yes.
680, yeah.
Oh.
Wait, the temperature of the roof tiles. The rest of the roof is covered with tiles. Oh, it's not 680. It's 80% of 680. Okay, so the second part is about the roof tiles only. It's got nothing to do with the solar panel anymore. So your roof tiles is like that, right? The 680 is coming in, right? Then of which 0.2 times 680 is how much? Huh? Sorry, no, 0.2. 0.2 times 680. 136. So 136 being reflected away. So how much is being absorbed by the roof tiles? 680 minus 136 or 680 times 0.8, which is 544, right? Watts per meter square. So for every 1 meter square of your roof tile, it will absorb 544, right? So at a steady state temperature, the roof tile must emit 544. Correct? Then you will depend, then you have to calculate, then that means this one here is 544. So 544 equals to emissivity of the roof tile times sigma times 1 meter, 1 meter square times T, right? So yeah, because 544 per meter square. Yeah, there you go. Yeah. Okay. Why do you have to do all that, leh? Okay. Yeah, this one here is missing the albedo. I wonder why he missed that one out. Okay. Then, okay. What's the next one? Real gas differs from ideal gas. Real gas particles have intermolecular forces. Nah, that one nah. Nah. Real gas have intermolecular forces. Particles, not real gas. Real gas particles have intermolecular forces. Ideal gas don't. So, like, what else do ideal gas not have? It don't have PE. Ideal gas PE is 0. Yeah, you can say that also, right? Then you can also say that the ideal gas, the internal energy is only the Ke of the particles. Yeah, you can say that. Uh-huh.
Potential energy is the intermolecular.
No. Okay, so I'm gonna ask you this. Two planets, do they attract each other? Right, two planets, huh? One, planet two. They attract each other? Right, so that's gravitational attraction, right? Okay, what's the GPE? Is it negative? It's negative. Good, right? So, how do you separate the two planets from each other? Correct, but do you have to do work? You have to do actual work, right? And if you separate them to infinity, what happens to the PE? What happens to the GPE? Becomes 0, right? Yeah. Then at infinity, what happens to the intermolecular forces? What happens to the gravitational force at infinity? 0 also, right? Okay, now you change the word planet to particles. Same thing. Same thing. So these are the intermolecular forces of attraction, right? And then the potential energy between the particles in a real gas is actually a negative value. So you know how we say ideal gas is 0? Yeah. Do you realize? I don't know whether you realize, but it actually means it has a maximum PE. It's ridiculous, right? You understand that? It's ridiculous, right? So whenever we say that, ideal gas have the PE is 0, right? PE of ideal gas particles is 0. It actually means that it has a maximum PE.
We are saying that so far apart.
And infinity from each other. Exactly. The volume of the gas compared to the volume of each particle is considered negligible. The volume of the gas particle is considered negligible. Yes, you're right. Right or not? Okay or not?
So there's no intermolecular.
Correct. You can yeah lah, correct yeah, correct So the question is this: ideal gas, can you buy it from the shop? You cannot, right? So you can only model ideal gas, right? How do you model ideal gas? No. You go and get a real gas. Then what do you do? What? No. Low density, low pressure, moderate temperature. That's topic 3 lah. No wonder. That's topic 3. That's why you all look at me blank. I was like freaking thinking like how come you all then don't recall? I haven't revised topic 3, is it? Just because I didn't revise it, that means you all don't know anything about it, is it? Basket, everything also I have to go revise it. Okay, fine. Okay. Anyway, so to make a ideal gas from a real gas, right? What you do is you give it low pressure, low density. That means you take out some particles. You take out a lot of particles. So it's like in a container of gas, right? Guys, if in a container of gas, right, you take out some particles, what happens to the remaining particles? They become very far apart from each other.
Oh, so that's why low density.
Low density, low pressure, correct. That's right.
Shouldn't density say that's related to pressure?
Yeah, I also don't know why also, to be honest. Yeah. I also don't know why. I mean, I don't know why they can't just say low density, like, but it's low density and low pressure. Never mind lah, just give them what they want lah. Huh? Okay, I don't know, I can't see why your answer is wrong. Right? Actually, I can't see why your answer is wrong. Oh, ew, okay, no, dude, what? No, 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 no. You're saying that the water volume expands and pushes and makes the air less. No, 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 dude. No, no. Okay, I'm gonna remind you this, guys, both of you. Solid liquid, right? When you heat it, it expands, right? They expand ever so minimally only. They don't expand by a lot one. Only gas expands by the most, right? So your reasoning of like, oh, so the water expands and push air out, right? Then left for less, right? Then not significant at all. The deal is with this, right? The particles gain KE, they move faster, they move out, right? They move out of the opening while keeping the pressure inside constant. So therefore, there's less particles in the airspace. Okay, because it's an opening, right? It's atmospheric pressure. It must maintain constant pressure, right? But then, of course, you might be thinking like, oh, but if less particles, how do you make the pressure the same? How is it the pressure is the same, right? Because they're moving faster, so they collide with more force. So the pressure inside is the same as the pressure outside, right? But the particles inside are moving faster.
Wait, for the pressure is actually for like the water surface or like the
All same, all same. On average, all same. Random.
wait, one you said that you say like when you heat the gas, you see the gas particle itself doesn't become bigger.
Yeah, it doesn't become bigger. It becomes faster. It gain KE, but the gas volume increase.
Because they move.
Yes, that's right.
So same goes if you heat a solid, the particle doesn't become bigger.
Yes, yes. Do you take chem?
Yes.
Okay, please don't say the particles become bigger. Yeah, because you're saying that the molecule become bigger. Like H2O, how does it become bigger? It can't become bigger. Just standard size. But they become faster.
They move.
So for particles, right, actually there's only two kinds of energy. Either they gain PE or they gain KE.
Oh, when they gain PE, they move further.
Yeah, when they gain PE, they can break away the forces. They can overcome the forces and become further apart. Yeah. Correct, correct, correct. Okay. The advantage of photovoltaic cell. Can store lor. I think you can store lor. Eh? Who asked me this question? You may? After the test, you asked me this question. Okay, okay. Why suddenly mark in green one? Benefit 得到 What the what? Why? Why? Specific frequency is heard either the source is moving away or the model correct. Bo liao lah. Sorry. Anything here? Anything here? No? This one? Number of slits increase, right? The angular doesn't change. It still stays in the same position. Because why does it stay in the same position? Because S equals to what? Lambda D over D, right? Then S over D is equals to lambda over D equals to theta, right? If you increase the number of slits, but everything else stays the same, right? The width stays the same, the separation stays the same, then the theta stays the same. So the angular position of the primary maxima will not change. It is a double slit, but unfortunately for you, right? I mean, they did say that these are all the primary maximas. These are all the primary maximas. Secondary maxima, oh, that's confusing. That's hella confusing. You see, the secondary maximas, right, is basically considered as a minima. Wow, this is damn annoying, because like you know why they didn't really explain this clearly lah. Right? You got 4 slits, right? 4 slits means what? 4 sources, right? Okay. The primary maxima is constructive interference of what? Of all the 4s. Of all 4 intensities, right? 4 sources, right? All these primary maximas are all, right? 4 slits. Hey, 1, 2, 3, 4. Right? 4 slit constructive interference. Okay? But how about the in between here? Now the in between here, right, is like 3 are constructive, 1 destructive. Or right in the middle there is 2 destructive, 2 constructive. Okay? And then to the other side is 1 and 3. So you see, right, all these secondary maximas are just your not completely constructive interferences, right? But if you add on more slits and more slits, right, all these regions here in between, they're all considered to be dark fringes already. Right? So the secondary maxima is supposed to be considered as a dark fringe. But it's very confusing because like you still call it a maxima. So I don't like this question. But I do believe that it's an IB question.
Also, when you add on more slits, does it mean there's more peaks?
When you add on more slits, does it mean there's more peaks? No. When you yeah, they just become brighter and narrower. Yeah. Because the dark fringes becomes wider. Yeah. Didn't I do this in one of the revisions? Yeah. No, as in like you have to remember what the effects when you increase the number of slits, right? So when you increase the number of slits, right, the 3 things that happen is the bright fringes gets brighter, the bright fringe gets narrower, the dark fringes becomes wider.
Oh, because if it gets thinner, then it makes more sense for the.
Yeah, the dark fringes are wider, yeah, that's right. But the reason why the dark fringes are wider is because if you have more slits, right? Let's say 8, right? Then it's 7 against 1. Then 6 against 2. 5 against 3. 4 against 4. Then 3 against 5. 2 against 6. And 1 against 7. So correct, more opportunities. Yes, that's the correct phrasing I use to, for like the I mean that's how I describe it. More opportunities, yes. Then the dark fringes becomes darker. Yeah, that's right. So this one here is super annoying. Like these are dark fringes now, right? So actually but they say intensity, right? So it does become darker. Yeah, because hmm? This is the double slit. No, I mean this is the multiple slits. Yeah, yeah. So it's going from double to multiple slits. Cannot. You okay? You can use d sine theta equals n. Okay, honestly, you can use d sine theta equals n lambda, right, on a double slit. But because the theta is small, right, it will naturally just approximate to d equals to n lambda. No, d theta, sorry. D theta equals n lambda. Yeah, d theta equals n lambda. Which is naturally is just this theta equals to lambda over d. Right? You can, right? You can. Yeah. Okay. What's the next one? 6b, yeah. Okay. Why suddenly got one from gravity becomes current one? What the confusing, yeah. Gravity becomes current. Oh, yeah lah, like I know, but no link one, might as well just put another question, right? Capacitor, why? What's up with capacitor? What are you doing here? You're charging the 24 microfarads, right? Okay. Then after that, so once you charge the 28 microfarads, then what do you do when you switch the switch over? Then this capacitor will discharge to this capacitor. Then this capacitor will charge up, right? So basically, so at the start, right, which one is charged? This one is charged. This one, no charge at all, right? The capacitor is 22 microfarads, but no charge at all, right? Then you switch it over. Once you switch it over, then this guy will discharge, and it will charge this guy, right? Okay. Then the question is, when does it stop charging? When do they right, when do they stop transferring charge to each other? When they have the same voltage. So capacitance is just this ability to capacitate. Like that's its innate capacity. So you can't change that one. That one is 28 microfarads, this one is 22 microfarads. You cannot change that, right? So the whole idea is that it will start off with a certain voltage, then afterwards once you switch over to this side, then it will discharge over to this side. So this side here, the voltage will rise, this side here, the voltage will drop, but they'll meet somewhere in the middle, and then they will stop, right? They will stop discharging to each other.
And
Yeah.
stop discharging the ball.
Yeah lah.
I thought they stop discharging when they have the same charge.
Then wrong. Correct or not? You understand or not? Do you know why or not? Do you know why they stop discharging to each other when the voltage is the same? No potential difference. But this kind of question always tricks students based on this. Okay, I give you hey, there's actually 3 scenarios, where these things happen. Okay, number one gas chamber, another gas chamber. Right? You open the valve. The gas moves from one chamber to another chamber. When does it stop moving? When it have the same pressure. One sphere, one charge sphere, another charge sphere. You put a wire in between. The charges from one sphere will flow to the other side until they have the same voltage. Until they have the same voltage. But charge sphere, right? What's the equation for charge sphere voltage? Yeah, lah, which one is it? Yeah, voltage. Yeah, KQ over R, right? For sphere. Then this one here, capacitor connected to another capacitor, right? The charge will flow. When does it stop flowing? When they have the same voltage. Potential, same pressure, then the flow will stop. Got 3 scenarios, right? Three similar scenarios.
Also same voltage for 2x.
Lah. Okay, but shall I do this question now? Okay, so all these are the correct answers. 0.042 millicoulombs. Okay, I tell you what, I draw it on my own. Okay, just remind me of the numbers, okay? Because I don't have the numbers with me. Okay, I got one capacitor. This one is fully charged now. Then this one is empty, right? Not charged, right? This guy is how many farads? This guy is 28, is it? 28 microfarads. This guy is how many farads? 22 microfarads. Okay. Which side is a positive side when it was charged? Which side?
The top.
This top part is positive, is it? Okay, why is that top part positive? How do you know? Yeah, because that's where the battery is, right? You see, that's where the connector to the battery, right? So this part here is positive. The bottom part is negative, right? Okay. So how much Q do you calculate just now? Like 0.042 millicoulombs, right? Yeah, 0.042 millicoulombs. Let me write it down again. 0.042 millicoulombs. This is a positive side, so it is positive 0.042 millicoulombs. On the negative side, what's the charge of the negative side? Negative 0.042 millicoulombs. Good question. Okay. Okay, what's this capacitor doing now in this picture? It's being charged. Let's say it's fully charged already. Okay, it's fully charged, right? What does a charging process entail? Absolutely wrong. Okay, what does the battery do to the capacitor to make it charge? Huh? Transfer, right? Is so the battery is basically pulling the electrons from the top plate and transferring it to the bottom plate, right? Correct or not? The capacitor initially was what charge? 0, right? So if you pull out one electron from the top plate, then the bottom plate gains one electron, right? And therefore,
But the charge stop is 0.
the Q is 0.042 millicoulombs, right? The value, the magnitude of it, but the top plate, one side is plus, one side is minus, because it was pulled from one side and then chucked over to the other side. That's charging the plates. Can? But now I connect it to another uncharged capacitor. Right? So what will happen then? Huh? What? Correct. Okay? So since the top side, so a bit of it will move over, and then a bit of it will move over like that. So at the steady state, right? When it's steady state, right, you will get, right, your two capacitors like that, right? The plus charge will be distributed on these two plates. The minus charge will be distributed on the bottom two plates. Okay, right? In fact, this is what 1.5 volts, right? 1.5 volts. So the final voltage here will be not more than 1.5, but above 0. So we somewhere in between. But we don't know what is it, right? We don't know what is it. So it's VF. Hey, I'm assuming that that's what the question asks. I never really read the question.
Okay.
It's asking for the final voltage.
They asked for that energy transfer. But I think it's
So no choice, you have to find final voltage one. One. You still have to find, like no matter what, you still have to find the final voltage. Okay? So now the thing is this, right? To find the final voltage, you can use, okay, so whenever you do this kind of question, right, what's the thing that you use to calculate? What's the most important thing you use to calculate? I know the final voltage is when it stops, but what do you use to calculate? You use the charge to calculate. The total charge will be conserved. Like what's the total charge on the two top plates here? Millicoulombs. What's the total charge on the bottom two plates here? Negative 0.042. So the total charge will be conserved. Okay. So what we're gonna do is we're gonna call this is Q1 final and this is Q2 final. Right. Q1 final plus Q2 final is equals to 0.042 millicoulombs. Right. Be it the top plate or the bottom plate, doesn't matter. Yeah, this one is the combination of both. But we also know that Q equals to what? Q equals to CV, right? Right. So C1 VF plus C2 VF equals to 0.042. Alright. What's C1? 28 microfarad. So 28 micro times VF plus 22 micro times VF equals to 0.042. Right? Based on this, you can find VF already. You can find the final voltage. Right? But after you find the final voltage, what do you do? Yeah, lor. So you go and calculate the half CV squared here. You go and calculate the half CV squared there, right? So this half C1 V squared VF squared, half C2 VF squared, right? So actually that's not the hard part. The hard part is this part, right? How do you calculate the final voltage, right? So like I give you a like a thing to remember, okay? Whenever you get this kind of question, your instinct is to find the final voltage. But how do you use to, what do you use to calculate the final voltage? You use the charge, right, to calculate, okay? Same thing for the spheres also. If let's say it's one sphere, another sphere, connect a wire, right? Your aim is to make sure they have the same final voltage, but you also calculate the total charge. Understand? Yeah, total charge must be the same, okay? How about the gas chambers though? Gas chambers, the final what is the same? Final pressure is the same, right? But then what do you use to calculate? Number of molecules, correct? Number of moles. Yes, you're right. Right? So same pattern one lah, right? Same pattern. Okay, but I leave this to you. That's not the crux of the question here. I throw in one extra one. Okay, I throw in one. What if you have two right, capacitors, right? Okay, just quick one. I give you two more scenarios. Sorry. What if you have two capacitors, right? But then they actually are both individually charged. Let's say this is like 2.5 volts and this one is like charged to 6 volts, for example, right? And the top of this plate here, there's a plus 25 micro lah, plus 25 microcoulombs, okay? and the top plate of the other one is plus 40 microcoulombs, right? Just random one like this. Okay, so you see this, correct? Like, what is the total charge on the top plates? 65. So your final, right, your final state, right, should be that they have 65 microcoulombs of charge, right? So you use that to calculate lah, right? Okay, but, right, got echo on, but. What happens if your scenario is now like that, same thingy, right? But then I go and reverse the plate. So this side here 2.5, this one 6 volts, right? I go and put this one here, the minus 25 microcoulombs on top, and I go and put the plus 40 microcoulombs on top like that. I connect the oppositely charged plates to each other. Then what's the total charge here? Right, it will be minus 25 plus 40, right? It will be positive 15 now, right? 15 microcoulombs, right? So after they distribute already, what's the total charge on the top plates? 15, no? Right? Yeah, 15. So it's still conserved. It's just that when you do this, right, you neutralize some charge, right? But the total charge is still conserved. So one side here, yeah, I mean the bottom side will be, I mean one side here will be plus 25, the other one is minus 14, right? Yeah, the bottom right will be, but when you do the calculation, doesn't matter. You just use a magnitude. Just use the magnitude. Yeah. Can
But that means
Ah.
the total and the final volume just I thought it was just 1.5. You see that was 8.5.
No, it's not. Absolutely not. It will not be equal one. In fact, one of the information that I did not tell you for these two questions, if you can see, right, is that I didn't tell you what the capacitance is. You see that? I only tell you the voltage, I only tell you the charge, I didn't tell you the capacitance. In fact, you can go and calculate the capacitance. You have to go and calculate the capacitance because you need it to calculate the last part, the final part. You need the C1 and the C2.
It's just cheap.
Yeah lah, something, I think maybe it's like 10 farads or something like that. I don't know. Something, yeah, or 0.1 farads, yeah. Okay, can?
So just now when you say energy transfer from the capacitor, we just take like what the field of time has
But because what we need to do is we need to find out what's the total energy stored, right? We need to find the total energy stored in each of them, right? We need to find the initial energy stored in this one, and we need to find out whether there's a difference. Like, will the energy stored in this one, right, be equals to the sum of these two final energies, or will these two energies be somewhat lesser? But obviously it can't be more lah, right? Yeah. Yeah, we expect it to be less. Yeah, it definitely will be less. Confirm one. You know why? Because when this thing discharges into the other thing, right, there will be a flow of charge. And when there's a flow of charge, there's always some loss of energy. Right? I can guarantee you that the final answer will be like the energy there will be more than the combined energy of these two.
Means the answer. The answer should just be the energy of plus C squared of initially minus the plus C squared of the C1.
No. Okay. So let me see the question.
Like transfer from the C1. So it means how much this one lost.
Yeah lah. No. So if they're asking for how much this one lost, right, you have to take this one, minus away these two.
But doesn't it transfer energy to C?
Calculate the energy transfer from C1. I would just calculate like what's the oh, you mean this one minus away this one, is it? Okay, yeah lah, yeah. Yeah.
Then the reason why
That means the energy loss from C1, is it? Yeah, okay. Energy loss from C1. Yeah. I thought you were talking about like the energy loss in the system. It's not. So it's this specifically only for C1, is it? Okay. Yeah.
the energy transfer
Yeah,
if any.
yeah. It will be. There will be loss. Confirm one.
So
Yeah.
half C squared equation in your lesson we said is half plus but when you're charging the capacitor there was heat loss.
No, no, no. What? Wait, what? What?
I mean
Wait, why is that? Wait. Are you asking about why is that half?
I said half C
Oh, because of the graph. So when you draw the graph, right? When you draw the Q and the V, right? When you draw the Q and the V, as you charge, right? The Q increases, the V increases, right? Then the amount of energy stored is the area under the graph.
so it's just
This just because of the area under the graph. Yeah, that's right. Yeah.
so it won't be C squared.
You know how let's say I have a 4 newtons force times 3 meters. What's the work done? 12 joules, right? Okay. But let's say, right, my force starts from 0. Okay, force starts from 0. Then after 3 meters, the final force is 4 newtons. Right? Then what's the work done? This is constant 4 newtons applied for 3 meters. The work done is 12. What is this one here? Start from 0 force. I begin with 0 force. Then I increase the force until it becomes 4 newtons, but it takes a distance of 3 meters. What's the work done by this case? Would it be 12? No, but would it be 12? Why not? Because it wasn't 4 constant, right? Okay, so the idea here is that force distance, right? You draw a graph up to 4, distance of 3, then it's the area under the graph. So it's half times 4 times 3, right? So the energy is, the work done by this one is 6 joules.
Oh, so the half C squared there's no energy loss, just like
Yeah, so the half CV squared is to help you. Actually, the equation, right, is QV, right? Then the area under the graph is actually half QV first. Yeah, then you substitute the Q with the CV, that's why it becomes half CV squared. Yeah, okay, can okay, next one. 7 Okay, I'm almost done already as in like I'm very tired already but I can do the rest next time, or you can just send me the question on your on WhatsApp. But please do the corrections in school. Wow, what the hell? What's this? Okay, what's the question itself? Which one is greater frequency? Is it? So obviously graph A is the greater frequency, right? But you have to explain why. You have to explain because it has a larger magnitude stopping potential, right? Larger magnitude stopping potential. Or you can say that the stopping potential is more negative, right? More negative, okay? I don't care what your teacher says. 4 marks, who gives 4 marks for this kind of stupid question, right? Then you have to explain why. You have to explain that, saying that, oh, when, since it has a higher stopping potential, right? Means what does it mean? It means that it was more difficult, right? Or it require, right? More, yeah. Basically, it requires more effort to stop the photoelectrons, right? Right, which means that the photoelectrons have more what? More Ke, right? Okay, and the reason why the photoelectrons have more Ke is what? Because the photon of light had more energy, right? The light photon had more energy. And based on E equals to HF, that was Einstein's model, E equals HF. That's what they mean, right? Based on E equals HF, the photon used in experiment A has a higher frequency because it has more energy. Yeah, like that. But 4 marks, walao, make people worry only. Yeah, but you are missing the, you know E equals HF Oh, you didn't talk about the electron. You didn't say that it was harder to stop the electron. You didn't say that the electron had more Ke. That's where your 2 marks went. Yeah, that's why you didn't get the full 2 marks. Okay, this one? Huh? Okay, this one. So the only first part.
C
And C, wow, the both of you a bit worried about C. Frequency of incident light is increased. 他妈的. Hey, you got two, sorry, pardon the French. You got two experiments. Which one is he talking about? Which one is he talking about? Never specify, right? I hate this kind of asking questions, stupid one. Okay, anyway. So frequency of light is increased. Let's say we talk about B, okay? Right? Let's say we increase the frequency of light, but the intensity remains constant. Then this is a problem, right? So when this happens, you know quantum, right? Quantum intensity, right? Okay, this is my last part for today. Any issues with paper 3 or not? Any big issues with paper 3 or not? What do you get for paper 3? Out of 80? 1-8. How come paper 3 only so short one? Oh, no astro, only the section A. Okay. So that one no problem. That one is quite okay. You know where your mistakes are. Okay. Line of best fit sometimes not straight line, no? Line of best fit can be curved. Yeah, you fool. Sorry. I didn't mean to laugh at you. But not curvy enough for him. Sad leh, damn sad. Huh? Smooth I'm going to drink beer lah, smooth. He wants smooth, ask me to drink beer lah. Getting me? So, intensity, quantum. Please remember this equation. Intensity equals to N over T HF over A. Remember this equation? N over T HF over A. N over T HF over A. What is N over T? Rate of photons. What is F? Frequency. Frequency refers to what? Frequency refers to what? Refers to the color of the light. N over T refers to what? How many photons per unit time, right? Okay. So you see, right? They want you to maintain the intensity, right? They want you to maintain the intensity, but yet they want you to increase the frequency. How? What is the compromise? You decrease the rate of photons, correct? Right. In order to keep the intensity constant, while increasing the frequency of the light, you must decrease the rate of photons. So you have to say that first. Then, okay. So you are right. Frequency of incident light increases, electrons emitted have higher Ke, the stopping potential will be higher, right? Okay, correct. But is that what they're asking for? Not at all. Right or not? So you're completely missing this part. They're completely missing this part. This part where I say that the frequency increase, the rate of photon decrease. So then you have to go on to the fact that, so in order to keep the intensity constant, when the frequency increases, the rate of photons must decrease, and therefore the rate of photoelectrons emitted is lesser, and therefore the current in the circuit will be lower. The current depends on the electrons. Allah. You want me to show you the notes or not? Yesterday someone asked me same question, no? He asked me like, oh, are we supposed to know this? Then I show you my notes down there. Okay, but okay, I understand, right? I understand. You're all just after your mocks, right? You're all maybe brainwashed out already and all that, but please try to gear up. Right? Try to revise all these things. You have to spend some time memorizing things. You understand, but you cannot recall. That's the thing that I noticed with you, right? So you need to recall. Right? You need to actively recall all these things that I've taught you before. Okay? And any last call for this one? Part D. Electrons emitted from photocathode has associated de Broglie wavelength. Explain what is meant by de Broglie wavelength. So it's a wavelength of particles which are dependent on the momentum of the particles. I believe you forgot to talk about momentum. Lambda equals h over p. Right? Lambda equals h over p. right? So it's associated with the momentum of the particles. The higher the particles, the higher the momentum, sorry, higher the momentum of the particles, the shorter the wavelength. That's right, there you go. Yeah, it's just a constant.
But isn't the momentum, isn't it relative momentum? Like,
That one is when you use the de Broglie equation on photons. Let's say, for example, let's say blue. What's the wavelength of blue? No. As in like, yes, but what's the wavelength of blue light? You're supposed to remember that. Violet light. What's the wavelength of violet light? 400, right? 400 nanometers, right? Okay, then if I apply the violet light here, can I calculate the momentum of violet photons? Can, right? Right, but does it make sense to calculate momentum of a violet photon? Why not? Because photons not supposed to have mass, right? So technically what you're calculating is relative momentum. Yeah, these electrons are particles, but they actually have momentum.
Yeah, actually,
They behave like a wave. Yeah, if I run fast enough, I also can behave like a wave. Okay? Okay, I go and find a document with definitions. This one need or not? Any part need or not? This one? Walao wei, this one, are they gonna tell you to connect this metal sphere to another metal sphere? Oh, don't have. Okay, what you want? This one? Define define electric potential. Work done per unit charge on a positive charge to bring the charge from infinity to a point in the electric field without a gain in KE. Because that's part of the definition. Dude, why is there an external agent? Why is the work done by external agent? Because that's just part of the definition. Right or not? I don't know what's your school's version. Did they go through this with you? Ah, like you go and look at answer scheme and see. You got the one. Oh, what the? What? Who gives 3 marks for this kind of thing? The pong. Hey, Dick, cannot lah. What you doing here? What's this? You lucky you get 1 mark. I haven't given you a mark at all. What nonsense? What's about? You can't experience potential energy.
No, but I thought you have the potential.
Yeah, correct lah. Then what you say experience? You can experience a force. You cannot experience energy. But you don't experience it. Okay? Can go and get your go and do your corrections. Go, two of you go and do your corrections. Okay, I'm going off now. Walao, damn late already. Good night. Bye.
Thank you.
Okay.